All right, off we go. So last time we finished section 2.3 on with 2.4. There's not a lot to say about it. This is mostly pretty readable. So please do take the time. Make sure that you're good with all of this stuff. What I do want to talk about is this first little bit right here. So I'm making the observation that differentiation is linear. Now, this is a lot more subtle than it sounds like it is. It sounds like I'm saying that the derivative transformation is linear. In other words, the act of turning input... good Lord, how did this thing die already? I don't understand that. Sorry, let me switch stylus. It sounds like it's saying that the act of turning an input change into an output change is linear. That's actually pretty clear. DF is a matrix after all. All matrices are linear. There's nothing subtle about that. Okay. That's not what we're saying when we say differentiation is linear. This means something significantly different. It means that the act, what D does, the act of turning turning a function into a matrix. Right? The act of taking an F and producing a DF. The act of differentiation itself. That's what I'm claiming is linear. Does everybody see the difference? Right? This is subtle. Right? This is where, having had a full course in linear algebra really is important, right? I mean, the idea of a linear transformation from a vector space of functions into a vector space of matrices, right, is something that takes a little getting used to. So anyway, that's the assertion. Said differently, the inputs to this linear transformation, D, right, the inputs are functions. And so when we talk about the linearity, we're talking about linear combinations of linear combinations of functions going in, not linear combinations of Euclidean vectors, right? Talking about linear combinations of functions and how the act of differentiation respects those linear combinations. So anyway, that's the one subtle part to this. Give yourself however much time is necessary to digest this idea. Here's an example that you can look at your leisure. That details for a specific pair of functions and how you take a linear combination of those functions. You see it right here. And how the linearity does what it's supposed to do. So that's very readable, I think. It's a good example to look through. And then now again, just a passing reference here, but there's also a product rule and a quotient rule in certain cases where it makes sense. So the act of differentiation has some nice tools. These are just rules. They're formulas. They're written down in the book. They're pretty straightforward. So that's something you can read yourself. Okay. Also in 2.4, higher order partials. And a lot of this is a pretty straight read as well. It's not really that sophisticated of an idea that, just like in single variable calculus, you have a function, you take a derivative, the result is another function to which you can take another derivative. Right? That's all it is. Right? So here, for example, here's a function, and I can take, let's say, the x partial of that, and oh my gosh, the result is another function. And so we can talk about, maybe taking an x partial of that. So no big deal there. I'm going to let y'all mostly read the notation. There are a couple of notations introduced here. I do want to point out one thing. It's a little bit confusing about the notation. Notation is, there's so many things about notation that are annoying. Sometimes when we indicate a notation for a derivative, we write it on the left, and sometimes we write it on the right. So for example, let's look at this function here where I have taken f and I am first doing an x, oh come on colors, first doing an x partial of it and then subsequently doing a y partial of that x partial. Well, the x partial is right next to the f, which is because it acts first, and then the y partial is right next to the x partial, so the y partial, the second one, is on the left. Because we write these down on the left, right? But notice when we use the Newton notation, right? But the colors, oh my gosh, that function, the Newton notation, the subscript notation, we put the derivative in a subscript, but on the right. And so the same derivatives, x partial first, written as a subscript. Right? Y partial second, written as a subscript. Now look at it. The y partial is on the right now, where it was on the left over here. And it's purely a consequence of the notations kind of being on opposite sides of the function. So, nevertheless, it does look weird. I mean, why is it yx up here, but it's xy down? These are the same exact derivatives applied in the exact same order. Nothing is different. But the notations seem backwards. And that's just the way it works. So, heads up. That's just something to pay attention to. All right. I'm also very quickly going to recognize here that, check it out, whichever order you do the partials in, whether you do the x, y, or the y and then x, whichever way you go, oh my gosh, what are the odds? Same answer. That's an eyebrow raiser. Right? Oh my gosh. How about that? Isn't that weird? Now you can look at the function in question and you can sort of think through, well, I mean, each term and then the power rule, and you can persuade yourself that this is actually not that surprising, certainly for polynomials. But it turns out that this is actually true for a broad category of functions. Lots and lots of different functions where it's not as immediately obvious because they're not polynomials and we can't just, sort of write down the power rule. So, in a very broad category of cases, this theorem holds, and this theorem is written down with clunky notation. It's there's no way around that. The notation just there's lots of different things that we have to refer to. So don't get intimidated or lost in the notation here. All this is saying is if you're taking a bunch of different partials and then you rearrange the order in which you exact same partials, but just kind of do them in a different order, then you'll get the same thing. Now, it's not always true. There are some obscure weirdo counterexamples. We're not going to see a lot of that in this course, if any. But nevertheless, let's talk about what the condition is on this working. The condition is that the function in question be what we call CK. So this is a really good thing to know. This notation is extremely common. It's a very important notation because in lots of areas in math, we need to be able to talk about, well, when a function is continuous. And we need to be able to talk about if its derivative is continuous. And sometimes we need to talk about if its second derivative, by the way, exists and is also continuous, right? So CK tells you how many partial derivatives, how many degree of partial derivatives do we know exist and are continuous. So K says the order of partials that have to exist, and C, colors, C is a reference to the fact that they also have to be continuous. Does that make sense to everybody? It's just notation. It just says how many times can you guaranteed take partials and take it to the bank that those are continuous. So now there's a gripe, a complaint, very reasonable complaint that you could make here, which is if I have to take all of the kth order partials and check that they're continuous. If I have to compute all these things anyway, I can directly observe when they are and aren't equal. So it seems like this is a dumb theorem. Like, how could this possibly have value? The answer is actually very, very simple. You don't have to compute the kth order partials. You just have to know that they exist and are continuous. So easy examples. If you have a function that's a product of exponentials and polynomials and sine and cosine, well, look, anytime you take a derivative, you're going to just be using the product rule and et cetera, and those things are going to move around, but you're always going to end up with another function that's a product of exponentials and polynomials and sines and cosines, all of which are continuous. And so you can, at a glance, in many cases, immediately confirm that the function is what we call C infinity. Right? So exponentials and polynomials and stuff like this are C infinity. You can take all the partials you want. They will always exist. They will always be continuous. Right? So you don't actually have to compute all of them. Does that make sense to everybody? Yeah.
What about trig functions?
Yeah, trig functions get yes, where they're defined, right? But we have to put that little asterisk in there. Like if you say tangent is involved, well, it fails to be defined in various places. But away from those places, no problem. Yeah. Okay. Alrighty. Here's where some non-trivial stuff happens that we're going to focus on and talk about. How do you visualize higher order partials? We're just going to talk about second partials. What do they look like geometrically? Now let me remind you a couple of sort of points of order. We've talked about the calculus of graphs. Right? The idea of calculus of graphs is that there are relationships between the algebra of the calculus, namely, how do you turn a function into its derivative, and what are the mechanics, the rules, all algebraic stuff. And then there's the question of, okay, what does that look like when specifically in the context of graphs? So this is really just that. We're going to talk about more calculus of graphs. And so another sort of point of order, as I have to remind you, don't forget, everything on this page is about graphs. And so everything on this page applies only on graphs, right? So none of what we're about to write down is in any way valid in reference to level sets of whatever function we're talking about. Okay, so this whole page is all graphs, nothing but graphs. All right, well, let's think about fxx, right? So that says we're going to take a function f, whose graph I've drawn, by the way. Let me indicate. So f, the graph of f is this, by the way, that's my effort at drawing a Pringle. I think that's pretty good. For this graph, this function f, what does it look like if I take the x partial and then the x partial of that x partial? How do I relate the geometry of that partial, or the geometry of that picture to the value, whether it's positive or negative, and vice versa? So, okay, well, here's the deal. If you want to take the xx partial, keep in mind the rule. Let's do it like that. The rule for taking an xx partial is everything else you treat as a constant. There's only one other variable. That variable is y, so we're going to treat y as a constant. So here's what it looks like when you treat y as a constant. Okay, we're going to take a cross section for that value of y. Said differently, we're kind of looking in the x direction, and then we're going to take that cross section and we're going to think about how can I understand that cross section. Okay, well, fxx says to that cross section we're going to take the derivative in the x direction Well, of course in the x direction. We've already agreed y is a constant. This is a function of one variable now, so I'm just going to say it's just the derivative of this function of only x. And then we're taking another derivative. So this is straight up, full stop, nothing more than the second derivative. This is just the second derivative of the partial function whose graph is that dark blue curve. And we already know how to interpret second derivatives, right, of single variable functions. Second derivative means concavity, right? So the fact that this is concave down means that second derivative is negative. Is everybody good so far? So now I said that in the language of the partial function, right? The function of a single variable only x. But now let's say it the full story in terms of the original multivariable function. fxx, whether it's negative or positive, is telling you about the concavity of the cross-section, vertical cross-section parallel to the x-axis. Does that make sense? And now there's an analogous argument, little analysis that y'all can do for yourselves. And I think, again, healthy exercise, and I hope you'll take the time. Think about what fyy would look like on this picture. Right? What's the process by which you take a y partial and then a y partial of that? As far as, on the picture, what does that look like? And then think about, well, what should that mean? And then notice that this picture, I'll just give you the punchline. The punchline is, it means that this curve, vertical cross section parallel to the y-axis, is concave up. And that is why we know this fyy is positive. Okay, I think this is pretty believable. I think this is kind of what you would expect, right? In other words, if I were to not show you this analysis and just say, why don't you take a wild guess as to what these things look like geometrically, you might have guessed this, right? It's very believable in that sense. It gets way weirder when you look at mixed second partials. So a mixed second partial would be like what I have here. Here I have a function f, to which I am first taking a y partial, and then second taking an x partial of that y partial. And I don't think it's particularly obvious or even sort of like, I don't even know what I would guess. Right? And I know the answer, right? But if I didn't know the answer, if I hadn't already seen this, what would you guess? What's the single variable analog of this? There is none. There is no single variable analog to the idea of taking partials with respect to particularly different input variables, because there's only one input variable. Right? So we are in uncharted territory here. There is no analog. There is no sort of piggybacking off of old ideas. And so we're going to really have to figure out what this looks like. Okay. All right. Well, this is, by the way, geometrically hard. It's very frustrating how hard it is to draw this picture. You see, I do have a picture going here, and my picture was... Oh gosh, this is the result of a lot of trial and error, where I try to draw a surface and then draw the relevant tangent lines and everything else that I need to explain this idea, and the picture always just ends up being too busy and muddled and confused. And I think the best way to understand this is I'm not actually even drawing the surface. But do keep in mind, we are talking about a graph here, and so in particular, we're going to, this is a picture of z equals f of xy, which of course means we're looking at a graph of f. Okay. I'm not going to draw that actual graph, but let's think about these partials, and let's just kind of do it one at a time. So I've got this function f, whose graph we are imagining, right? And now let's ask, okay, how would I understand the y partial on this picture? What do y partials of graphs, y partials of functions look like on a graph? And that's old news. Y partial means that I'm going to look in the x direct. Oh, come on. In the y direction, because we're taking a partial with respect to y, and we're going to look at the cross section vertical cross section in the y direction. Look at the corresponding tangent line to that cross section, and so the y partial is this slope. If I were looking at this point, the y partial is the slope of that line, right? Again, kind of old news. Everybody with me so far? Okay, here's where it gets weird. I can't think about the x partial in terms of cross sections and slopes, because, very importantly, I'm not looking at a graph of the y partial of f. It's as simple as that. We're looking at a graph of f, right? So we agreed upon that at the beginning. We're looking at a graph of f. I can only interpret a partial as a slope of a cross section if I'm looking at a graph of the thing I'm taking the x partial of. I am not looking at a graph of the y partial of f. I'm looking at a graph of f itself. If you're not looking at a graph, forget about slopes and cross sections. It's just not what it means. So we're going to have to find a different way to make sense out of this. What does this x partial mean? What other tools do we have for understanding x partials? And the one I'm going to use here is, it says, okay, well, yeah, but how, as I move in the x direction, how fast is that thing changing? Right? So that's what we're going to try to represent here. I'm going to say, suppose whatever point I'm at, let's say this one. As I move in the x direction, how fast are these y partials changing? Right, and so now I've drawn some, again, I have not drawn the underlying graph. The picture just gets ugly. But I've drawn various of these y partials, various of these tangent lines in the y direction representing y partials. And let's just kind of talk about some numbers here. Approximately what does this look like? And I'm going to say this one here, back in the far back, that looks like it has a slope of about -2. And then this one's about -1. And this one's about -0.5. And this is about 0. And this is about +0.5. And what you notice is that as you go in the x direction, these y partials seem to be increasing. Everybody see that? As I move out of the screen, as I move in the x direction, the y partials that were really negative, well, as I go this way, those very negative slopes are turning into less negative and then eventually positive. Those slopes are increasing. So how fast are these y partials changing as I move in the x direction? In other words, what is this x partial? Well, it appears to be positive. Right? So the conclusion I would have, if this is what the picture is, if this is what these tangent lines look like, I would say that, I would say that this x partial of the y partial appears to be positive. Everybody buy it? So it's geometrically challenging, isn't it? There's a lot to kind of digest and think about. Most confusing for me personally is that I've got two different partial derivatives and I'm interpreting those partial derivatives with different tools at the same time. I'm interpreting the y partials as slopes. I'm interpreting the x partial as a rate of change. And so you just gotta be sufficiently comfortable with these different interpretations of partials that you can simultaneously think about them in these different ways. Yeah.
So every time we come across like an x and a y partial together, is this how we're going to be interpreting it, or is there like a specific, like, does it vary case by case?
Well, I mean, there certainly are various different kinds of pictures. I mean, it won't always be this picture, and this x partial or the y partial won't always be positive, right? Depending on the function, depending therefore on the graph, it might be, the sort of twist that you see here. If the twist might be the other way, or it might not twist sort of beyond the horizontal. It might twist further vertical. Or it might twist but never quite get... I mean, yeah, it'll always be a little bit different, right? But this is, as you know, I like to say, this is a tool for your toolbox, right? I'll say this is the only visualization tool that I'm going to give you for mixed second partials. Yeah, right? But I hesitate to say that it will always be exactly what you need. Yeah, right. Yeah. Okay, how we doing? Everybody all right? Okay, by the way, this is called torsion, and as I just kind of demoed with my hands, I like to think of this as a kind of a twisting, right? I mean, what I see when I look at how these tangent lines, I see like there's a flexible surface that's been kind of twisted. I don't know if y'all can see what I'm doing with my hand. Imagine that I have a sheet of rubber that I'm grabbing onto the corners of, and I feel like that sheet of rubber is getting twisted like this. All right. Okay. Moving along, let's talk about section 3.1. So we're done with 2.4. By the way, real quick, this is one of the moments in the course where I do a little bit of bouncing around through the book. You'll notice we have not finished with chapter 2, but we're going to do section 3.1. I like to use a point of view on derivatives described here in 3.1 when I explain section 2.5. And so Kali doesn't feel that need. I like to explain it a different way. I need what's in 3.1 before I can do 2.5 the way I want to. So thus the reordering. And this is perfectly fine. There's nothing else from chapter 2 that we're going to need to make sense out of 3.1 here. So it doesn't matter. Okay. Parametric curves. All right, we've talked about those. Position is a function of a single parameter. Usually think of that as time. Might as well. So position is a function of time. That's what a parametric curve is. Okay. All right. Let's see if my other stylus is back in business yet. Yep. Hopefully I can make it through class. Okay, so let's talk about the derivative matrix of a function like this. You take several outputs, means that I will have several rows. I have but a single input. That means that I have a single column. So interestingly, when you have a parametric curve, the derivative matrix is a single column matrix. Which, by the way, very commonly, nice to think of as being a vector. And in fact, that's a really nice way to think about it in this case. So if you were, in fact, to think about the single variable definition of a derivative, right? Flashbacks, everybody remember this formula? Right? This strategy for talking about a derivative makes perfect sense. There's a single input variable, so the denominator is a scalar. There's no reason we can't use this idea of a derivative for a parametric curve. And notice everything in this formula is computed one coordinate at a time. So in fact, the derivative matrix that you get is the same as the what you would get if you were to apply the sort of the old single variable calculus definition. So kind of nice fact. And I can totally just start drawing pictures of what's going on here. We have 2 points, like there and there. You know, where am I at time t and where am I h seconds later? And I can look at the difference. Well, we know how to do a difference. That's a subtraction. That's what a subtraction looks like, right? On a parametric curve. And then I can talk about the limit. Well, let's see here. We'll, divide by h. That's going to scale this in some way. And then in the limit, these points are going to get closer and closer together. These purple vectors are going to be getting smaller and smaller, but I'll be dividing by smaller and smaller h's. Y'all have been down this road before, right? And presuming that the functions in question are nice, we would expect that these vectors in the limit would approach something like that. And again, flashbacks to single variable calculus. In single variable calculus, we're looking at the slopes of these lines. We're not looking at slopes of lines here. By the way, we're not looking at a graph, are we? That is a parametric curve. There's no t-axis. This is not a graph, and we cannot interpret this in the way that we interpret graphs. So forget about tangent lines. But nevertheless, we've got these 2 points, and we're looking at it's a vector, not a line, but we're kind of looking at the line between them, and in the limit, as they get closer and closer, these, you may remember the term secant lines, in the limit approach a tangent line. Right? And so, what you would expect generically is that this vector would be pointing in the direction that the curve is going. It'd be a tangent vector. So the direction that that points is the direction that the curve is going at that instant. So tangent vector. And then, by the way, let's think about the magnitude in the limit. What we're talking about here the magnitude of that numerator is distance. The magnitude of the denominator is time, and distance per unit time is speed. So I think it's a pretty easy pitch that what we have here, this dx dt, is pointing in the direction that the curve is going, and with magnitude equal to speed, that is the very definition of velocity. All right, so flashbacks again to when would you have seen this? Probably in very early in Math219 when they're talking about vectors. What are vectors? Direction and a magnitude. Velocity is one of the classic sort of first examples. So this is a really nice result, and I made the assertion earlier that viewing this as a vector would be very natural. Absolutely, it is very natural. It's the velocity vector for the parametric curve for which this is the derivative matrix. Is everybody cool with that? All right. And so the derivative of position is velocity. Likewise, the derivative of velocity is acceleration. I'll say etc. But those are really the only two in most cases that you need to deal with. Okay, here's a fun. I actually just learned this in the last few months. This is a very recent thing for me. Someone pointed this out. There's nothing hard about this, but since I never quite made the connection, I think this is really, really nice. So y'all know the unit circle, right? Definition of trig functions, ancient history, old news. Okay. So position, if you want to think of as being position vector, suit yourself. Position, x and y are the definitions of cosine and sine, and so the formula for the position there is cosine comma sine. The way we define t represents that distance. It's the distance along the curve. So the distance covered per unit time is distance per unit distance, which therefore means the speed is 1. So what we have here, when we say that, we're looking at a parameterization of the unit circle by cosine and sine, that is a parametric curve going around the unit circle with unit speed. Okay. Okie dokie. Well, we just learned that the derivative is the velocity. And in particular, that the derivative is a tangent vector. And so looking at this picture here, if that's a tangent vector, by the way, the speed being 1 means I know that this magnitude of that velocity vector is 1, right? And the fact that it's a unit circle means the magnitude of the position vector is 1. So those two hypotenuses, that doesn't sound right. Anyway, that hypotenuse and that hypotenuse have the same length. These are therefore similar triangles. A little flashback to high school geometry. These two gray triangles are similar triangles. In fact, they are what's the term? Equivalent. They have all the same. Congruent. Thank you. These are congruent triangles. And that means that their lengths correspondingly are all the same. And that means I can straight up write down what this velocity vector is. This velocity vector, just looking at these edges being the same as those edges, the velocity vector is that. Right? You got to think through the trig, and don't forget that we're going sort of backwards in the x direction, thus this minus sign. Okay. All right. But wait a second. We also know that velocity is derivative. So, okay, let's put this all together. Position, which has these coordinates, if you take the derivative, and of course we take derivatives one coordinate at a time, we know that the result will be the velocity, which we just argued here. And so check it out. I did not have to assume prior knowledge of how to take a derivative of cosine or how to take a derivative of sine. We have shown. Right? No fancy arguments in single variable calculus, like, where you look at the limit and there's kind of a little detailed argument that shows that the derivative of sine is cosine and et cetera. Here we have a purely geometric argument that shows that the derivatives of cosine and sine are what we knew from Calc 1 that they are. I think that's fabulous, right? So, much easier way to show what the derivatives of sine and cosine are. Just merely knowing that derivatives are velocities and applying appropriately to this circumstance. Okay. All right. Okay, here's another example. This pretty straightforward, but let's walk through it. Suppose I give you a velocity, and then I ask, well, what's the acceleration? What's the position? All right, well, acceleration is the derivative of the velocity. So, take the derivative, boom, there's your acceleration. Kind of boring. What is position? Okay, wow, let's see, I'm going to have to think about that. Position, okay, the derivative of position gives you velocity. So if you turn that around backwards, position is the antiderivative of velocity. Is that cool? So that's all I'm doing here. Taking, again, the same velocity that I was given, and I just take an antiderivative of velocity, because velocity is the derivative of the position. That might even be familiar, right? Y'all did probably something very like this in a Calc 1 class. Okay. All right, so then you have to, how do we take an antiderivative? Well, we do it one coordinate at a time. Ancient history, antiderivatives. By the way, make sure you're good with all the anti-differentiation rules. integration by parts, substitutions, all the stuff. By the way, we're not going to use any obscure weirdo anti-differentiation examples or rules, right? But integration by parts and substitutions are they're everywhere, right? Can't get away from them. So I am going to assume the final exam will assume that you are proficient and polished on that and other basic anti-differentiation stuff. So make sure you're good with that. Okay, and then let's not forget, of course, when you take antiderivatives, don't forget your plus C. Now, here's where a lot of students mess up. A lot of students crash and burn. What's the plus C? Oh, hey, wait a minute, check it out. We were told an initial position, an initial value. A lot of students mistakenly think that the initial condition is the constant, and that is nonsense. Why do students think this? Because there's a lot of coincidences that happen in which it is. But it's just a coincidence. And by the way, there are a lot of high school teachers out there telling students, the integration constant's always equal to the initial condition. Because maybe those high school teachers have simply not noticed that the fact that this happens surprisingly often is purely a coincidence. Okay, as a rule, this is not true. It's just not true. And I deliberately set up this example so that it would not work out with that coincidence. So let's think about how to show this. Well, we're going to look at this equation where I have these three things. We're going to plug in t equals 0. I'm just going to plug in t equals 0. Well, when t equals 0, my initial condition is that r of 0 is 5, 6. When you plug in t equals 0, that turns into that. That's just arithmetic. Right? Plug and chug. And so this constant that I'm trying to understand, I can't plug in for it, of course, but that constant I'm trying to understand, when I plug in t equals 0, that purple equation turns into this dark blue equation, and then, of course, it's very easy to solve for c. So that's the process, right? This is how you evaluate that integration constant. You got to plug in for your initial condition and then solve for that thing. Notice, very importantly, let's see here. I guess I have to shrink. Notice, this constant is not the initial condition. So I want to just be emphatically clear about that. It does not give you the right that the initial value, the initial condition will not in general be your integration constant. Now, why do students think that it is? Aside from their teachers having tragically told them this nonsensical falsehood. And the reason is there's a large category of functions, polynomials, that have a peculiarity. And the peculiarity is that this, for polynomial, if what you start with is a polynomial, that expression will have a factor of t in every term in that expression, and this will, in that special case, always be 0. And if that's 0, then the initial condition will turn out to be your integration constant. But that's a peculiarity of polynomials. Polynomials are absolutely not the only functions out there, right? It's just not the way the world works. And so as a general rule, this is just not true. Does that make sense to everybody? Everybody happy with? So I want to make one other thing clear, and I know I say this a lot, but I say it a lot because it's really, really important. This is a class about ideas, not answers. Mathematical reasoning, not results, right? So the purpose of my gripe here is not to point out, hey, you're going to get wrong answers. Well, yeah, that's true, but that's not the problem. The problem is it is invalid reasoning. right? Sometimes invalid reasoning gives you correct answers, as we see with polynomials. Don't care. Right? The point to this course, the way you're going to be graded on exams, it's not about whether your answer is right. That's just not the point. That's not what this class is about. Right? The question is your reasoning valid? And if you write down a integration constant and just by saying, hey, this is the initial condition, so it's the integration constant, and coincidentally you happen to be right, doesn't matter. The reasoning is wrong, and the scoring is based on the reasoning. Does that make sense to everybody? So just, something to keep in mind. Okay, I'm going to point out that while most of what I'm going to call the Kepler stuff in this section, there's all tedious, lots and lots of calculations that relate to the historical, how Kepler came up with his laws of planetary motion, and it's cool math, and it's fun and interesting and historically relevant and kind of fascinating in that sense, and it's too tedious for this course, and we're just not, you're not responsible for that stuff. I mean, give it a look if you're curious, but you don't have to. But there is one thing in there that we really do need, and that's this proposition 1.4 right here. So do make sure to see that. By the way, it's I'm going to call this good news. It's good news in the sense that when you take derivatives of products of vector-valued functions, be they dot products or cross products, there's the product rules that are exactly what you would hope that they would be, right? So it's very nice, but just because something looks like it ought to be true doesn't mean that it is, so we have to appreciate that it actually is, in this case. Okay, yeah?
Should we be responsible for kind of understanding both of these, like visually or like as a picture?
I would say it's a little hard to get a geometric intuition for these, other than you can draw a picture of two vector-valued functions and you can try to get some sense for their dot. But that's not really the way I want you to think about them. The way if you wanted to show that these are true, the way that I understand these results is that I know how to take a vector-valued function and write it in coordinates, and I know how to write out a dot product. And then I have a bunch of terms, and I know how to take a derivative of a bunch of terms, and you just do it one term at a time. And what you'll find is that if you do that, oh my gosh, you get exactly the same thing as if you had done the same overall, right? It's just, work it out in coordinates, and it just works. And likewise there, yeah. So these are algebraic tools primarily. Just use them as algebraic tools. Okay, let's see here. We have a couple of minutes left. I want to plant a thought. This is a single variable calculus thought. There's many different ways to think about single variable derivatives. By the way, very often in this class, we're going to find that there is a particular point of view, be it on derivatives or integrals or what have you, a particular point of view that is uniquely convenient for our purposes at a given point in time. So I know that this is probably not your favorite point of view on what a derivative is, but this is the point of view we're going to need for what we're doing here. A derivative is a factor that you multiply by an input velocity to get an output velocity. So yes, it's also a slope. Yes, it's also a blah, blah, blah. Right? But this is the way I want to think of it here. Make sure you're comfortable with this. A derivative is a multiplicative factor. It's what you multiply by input velocity to get output velocity. Now, with that point of view, here's what happens when you compose two functions. Here's a single variable function. Y is a function of x. Here's a single variable function. Z is a function of y. And when I compose them, I get a single variable function where z is a function of x. So there's three single variable functions on the page here. And I'm going to just point out that if there's a factor that I multiply by x prime to get y prime. And if there is then another factor that I multiply by y prime to get z prime, right? And then if I asked, oh, okay, well, what then is the resulting overall factor that I multiply by x prime to get z prime? Well, let's see here. I multiplied by one factor and then another factor. Altogether, you can multiply by the product of those two factors. Does that make sense? Everybody buy it? And again, there's a bunch of different ways to think about the chain rule. I know that. I know this might not be your favorite way to think about the chain rule, but this is the way to think about the chain rule that's going to be most useful for our purposes. And the derivative of the composition is the product of the two individual derivatives. Colors. Product of the two individual derivatives, because multiplicative factors multiply. And we're going to pick up here next time and generalize this to a multivariable setting. Y'all have a good rest of your day. See you later.